Hi folks, this is Tom. Today I'm going to show you the GenRad model 1863 Megohm meter. These are a really cool device. I originally used these at my last job when I was in the relay industry, and we used these for measuring super high resistances. This particular one here essentially goes from about 50,000 ohms. It goes to 1 tera-ohm up here. Let me run the voltage up. There you go, 1 tera-ohm, and it'll actually go up to technically to 20 tera-ohms right there. So you can measure all sorts of stuff, all sorts of high resistance here you could never measure with a standard voltometer. Okay, let's check a few things here. Okay, we're back. This is a Sprague 0.04 microfarad 1600 volt DC buffer capacitor. This is used to basically take the high voltage sparks and shunt them across a vibrator type power supply. And what that does is it keeps the relay contacts from charring. So these are fairly high breakdown voltage here, 1600 volts DC. Let's go ahead, and what we're going to do is we're going to put a full 500 volts on this. Now we're going to go up here. This is going to charge up. It's on 1 meg. Okay, that's there. Now what we're going to do is we're going to run this up. Okay, we're starting to see some at 100 megohms times 20. That's a 1 gig scale. So right now that capacitor is about 4 gig ohms. And you can see right now the needle is slowly but surely going up. What's happening is you've got some dielectric absorption and some polarization going on. So it may take a while for this thing to reach its final value. The important thing is, though, that at 1 gig ohm plus with 500 volts on it, that this capacitor works. And that's all we need to know right there. We can actually kick this up to the next scale. If you look, we're more than 5. And if you see the scale over here, it starts at 0.5. So if we kick the next scale up, it'll be 0.5 plus something. Let's go to the 10 gig scale. There's 10 gig, and oh boy, look at that. Right now we're at 9 gig and counting. So we're going to call this capacitor good, at least as far as leakage goes. Let's go to another capacitor. Okay, here we go. This is a Sprague vitamin Q capacitor. That's got a 0.043 at 400 volt DC rating. The cool thing about a vitamin Q is that this is the only paper foil cap that probably is any good. You can see these are in metal cans, glass ends on them, so these are nicely insulated. The deal is that these are actual real paper foil caps, and again, the deal with this is that paper foils, they all leak. Atmosphere gets in, the paper oxidizes, and it gets sulfuric acid on it by the action of the air on the sulfite paper, and you get resistance. The vitamin Q was essentially the last generation of paper foil cap. They figured out how to make them work, and here we are. We're anywhere from 70 to 60 years later, and a lot of these are still good. Let's check this one for leakage. Okay, since this is a 400 ohm cap, we can't go 500 volts on it, but we can go 250. That's the neat thing about the 1863 here, is you can go 50, 100, 200, 250, and 500 volts. Let's see, standard resistor testing and component testing is typically done at 100 volts, and insulation tests done at 500. So this supplies both voltages that you need for industrially testing something, which is cool. You've got these other little divisions in here in between. Okay, here goes. We're going to charge this up. 1 meg, that's fine. And now what we're going to do is we're going to go up, go up, go up, go up. Wow, we're at 10 already. And yeah, let's go back down again. It's charged. There we go. Now the handle's up. And here we go. We're just starting to move now at 100 gigs. So if this is 100 gigs, roughly. We're sitting there, 100 there, full scale, 300. So this paper foil cap, which has got to be probably at least 60 years old, has no leakage on it to speak of, so it's good. Let's discharge this now so we don't zap ourselves. The cool thing about the 1863 is that, let's say you have an unfortunate accident and you wind up becoming part of the circuit here and shocking yourself. This is limited to 5 milliamps output current, so you'll definitely feel it, but it should hopefully be hazardous to you. Let's check this out. This is my trusty Simpson 260. It's on the 10 milliamp full scale setting. We're going to kick this up here to charge, and see, we're charging right now. And so we've got 500 volts on this. At 500 volts, we have, guess what? 5 mils. And of course, that shows that this is a dead short. Yeah, at least as far as the meter is concerned, the 1863 that is. Let's go ahead, we'll just put this on charge, and we're going to go down to 250, and that shows a little bit less there. That's about 3.6 mils. 200, that's still about 3.6. 100, we're still about 3.6, and we're still about 3.6 right there. So it looks like, other than the highest scale, we're sitting at about 3.6 mils, and that's fantastic. So, you know, it's not going to hurt, it's not going to kill you like if you came across a very high voltage supply that has serious current behind it. Still, don't get unlucky, and try not to let it zap you. Okay, folks, let's do something practical. This is a cool NOS transformer. Not sure what type this is. It's still literally in the package here. This is probably, at this point, 70 or 75 years old. What we can do, though, is look at this, and there's a standard chart for these colors here on a transformer. This is the 1964 Amateur Radio Handbook, and we're on page 510. These are real good to have if you don't have any of these. I collect these, and I've got quite an assortment of them. There's all sorts of incredible information in here. Okay, so the primary leads on this transformer are black. So you've got the black here and a black down there. So that's primary. That's going to probably be 110. High voltage plate winding is red, and the center tap is red yellow. There's our reds, and there's a red yellow right there. So we know that that's our high voltage winding. And the rectifier filament is yellow. And let's see, so we've got two yellows right here. That's these guys. And then green is going to be your actual filament windings for whatever this device goes to. Typically, a standard electronics drop-in transformer, you're going to have a high voltage, possibly 150 to 300 volts in here. Your rectifier filament is probably going to be 5 volts, typically a 5Y3 or a 5U4. And then your secondary winding for the filament's probably going to be 6.3. It may be 12.6. And that's basically it right there. So we should be able to do with this is check between the windings here to make sure that there's no shorts. And if we have access to the case, we can actually clip onto the case to make sure that none of these windings are connected up to the case. But we'll check the windings here real quick. Okay, we checked here between the high voltage winding and the input. So let's go ahead. We're going to do 500 volts on this one. Started a Megohm down here. Oh, yeah, there we go. It took a little bit of current. It charged up. And now we're going to crank this. Oh, we're starting to see a little bit of current being drawn at 100 mils or 100 megs. 1 gig is right there, 1.5 gig ohms. Honestly, that's like zero leakage between them. That's a very, very, very high figure. So I'd have no problem at all connecting this thing up and knowing that the high voltage is not going to short out to the input. Okay, now I've gone from the high voltage to one of the rectifier windings. You see that charged up momentarily. And again, we're sitting about 4 gigs right there, 4 gig ohms. That's a big thumbs up right there. Let's discharge that. Okay, we're back. Let's go ahead and we'll check this, and this is from the high voltage to one of the rectifier windings, and right now you see we're well over 10 gigs there. Let's crank this up to the 10 gig mark, and you see right there we're about almost 14 gigs. Again, there's no leakage to speak of right there. This is fantastic. We're going to go ahead and stop the test here. If we're going to do this exhaustively, we would test between all of the different windings to ground, but this is a good check right here. This is what you want to do before you take something like this and put it into service. Okay, we'll discharge that. Safety first. Okay, folks, we're back. This is an interesting device right here. This is a neon sign transformer. Let's see, it's got 115 volts input at 0.6 amps, and it's 3,500 volts on the secondary at 15 mils. So this can definitely shock the living crap out of you, and it's definitely useful for any number of things. What I'm probably going to do with this is to put the insulating pieces back in here, and we're going to put it back together again, and I'm going to actually use this to high-pot tubes, high-power transmitting tubes, to make sure that there's no gas in them. Okay, if you look, this is the really thick wire. That's the secondary, the high-voltage side. So that's the 3,500 volts right there. So we've got one there, and this is the other set of wires here. This is the input. So what we're doing here is looking input to output. And we definitely want to check this thing at the highest possible voltage that we can. So we're going to be at 500 volts, charge it up, boom. It took a little spike there as it charged. And there we go. Let's go up here. Oh, look at that. Right there, we're at about 1.7 gigs. And you can see it's very, very, very slowly climbing up due to dielectric absorption there. Okay, so we see right now that essentially there's no path between the secondary and the primary, so that's good. Let's check and see what the different windings are to ground. Okay, we're going to switch to safety, turn this off, and now what we're going to do is we're going to take the input here at the 110, and we're going to go to ground, kick it back on again, and that one quick blip as it charged, and there we go. And right now, 110 volts to ground. And right now, we're looking at, there's 1 gig. So that's 1 gig, 1.2 gigs. That's perfectly fine. No worries at all with that. Let's switch back to safety, shut that off. And now let's go to the 3,500 volt tap. And we're going to go to ground. And uh-oh, we have a problem, Houston. Let's go look at this. If we look at this, this is probably the worst case scenario right here. You actually have 300 megohms to ground leakage on the high voltage side. So this is where it's likely to fail. This is where we can pull an old Hallicrafters trick up. The Hallicrafters SX28 had issues with it where the transformers were junk. The audio transformer that typically had your full B plus on it, it would short from one of the windings to the case. So the trick there was to put the transformer case on standoffs, and that way you could still use a shorted transformer because it wasn't completing the path to ground. So what I'll do with this one here is, this one is going to go on a piece of plexiglass, and that way if we go again to 1.2 gigs or 1.5 gigs versus 300 megohms to ground, we've got the best chance of surviving right there. So even though this is lower than I'd like to see it, it'll probably work fine, but I don't want to have any unfortunate things happen. So if I put this into intermittent service and put a variac on the input and use this to go up to 3,500 volts to high pot tubes, that's a great use for this. Okay, another good use here is to check out Geiger counter parts. Geiger counter parts are very high voltage. They can have up to 1,000 volts, sometimes more on them, and you want to have super, super, super low amounts of leakage. The only way to test that really is with something like this. This is a transformer high voltage transformer. This came out of either, I think it was a Lionel 6B. So I believe the Victorine 6 and 6As were different. So let's call this one a 6B Lionel. If I got that wrong, I'll put it in the footnotes. Okay, here we go. We're going to put it on 1 meg here to start it. It charged up, and there we go. Now we're going to turn this up. Oh, we're starting to see it move a little bit. 1 gig is there. That's 5 gig ohms, and it's slowly working its way up. Beautiful. I would say that winding there to the other winding is good. Let's go ahead, switch to safety. Okay, we've gone from the winding now on this side to the other winding on the other side. So let's check this out here. Okay, it's charged up. And there we go. That one is 8 gigs, almost 9 gigs. Let's check the windings here to ground. Actually, before we check the windings to ground, let's check these other 2 windings to each other. Okay, we're going to start at 1 gig here. Boom, there's our little impulse, and there we go, right there. We're about just shy of 4 gigs. I'd say that's good there. Let's check ground real quick. Okay, we're back again, and here we go. Wow, that's not bad at all. That one is 15 gigs between that winding and ground. Switch to safety. Okay, we've put the other winding to ground. And there we go. That's quickly going up to, that's a 10 gig. We're at 20 gigs already and climbing. That's fine. Let's check the last one. Switch to safety. Okay, we're back over here. Let's check this out. And, okay, there we go. 10 gigs. So there's 7, 8. It's coming up. That transformer's fine. Let's switch to safety again. Okay, this is a high voltage diode from a Lionel Model 6B CDV 700 Geiger counter. Let's go here. We're checking it not forward but backwards to make sure there's no leakage through it. 500 volts. Okay, we saw the impulse. Let's crank this thing up, and there we go. Right now, again, we're coming up to about 5 gigs right there. That one's perfectly fine. Again, switch to safety here. Okay, what we have now is we have 0.01 microfarad, 1.4 kilovolt caps. These are the high voltage filter caps that you have in a lot of your CDV 700 Geiger counters. Okay, let's go back up to here. We'll turn that down, turn this on, put voltage on it. We saw the impulse there, and let's crank this up. And right there's 1 gig. Oh, wow, we're well over 10. Right now we're at 15, 19, 20 gigs and counting. Yeah, I'd say the cap's fine. And let's switch to safety again. Okay, here we've got a rogues gallery of blocking capacitors. These are high voltage caps that were used in World War II transmitters. These would block the DC, and what they would do is pass the RF, and that would allow the RF to go to the antenna. Okay, if we look at this, this one says it's 35 megohms, June of 2000. So this has been well over 25 years since I've measured this. So let's go check and see how time has treated this. And you guessed it, yes. The last time I tested it, it was on one of these GenRad testers, although it was probably the 1862 Charlie or the 1862 B as in Bravo. Okay, so if that was 35 megohms, we're going to start on the 1 megohm scale here. There we go. Saw the impulse there, and turn this thing up. And, stand by. Run it up to there. Wow, we're on the 1 megohm scale, and we're already a little over 10 megs leakage. Let's see where we're at. Okay, fast forward 25 years, we're sitting almost at 1.2 times that, or 10 meg scale. So that's 12 megohms. There we go. Turn the power off so we get zapped. So here we go. This is a silver mica from World War II, and 25 years ago it was 35 megohms, and now it's about 12. So this one's definitely circling the drain. Okay, here we go. This is another capacitor blocking cap. This was, I think I measured at 1.8 gigs, again, back in the year 2000. So let's go check this out. We're here, and we're at 10 megs. Put it back down there, and okay, crunch this up here. We're starting to see it leak. And there's 1 gig, and then there's 4. Whoop, yeah. So it looks like we're sitting at about 4 gigs. So this one actually hasn't done bad, and it tests better now than it did in 2000. So maybe this thing has dried out in the meantime. Now it's passed this test. So theoretically what I could do is I could actually run it over here. What we can do is test the capacitance on it. Or we could stick it on the Sprague Tera-ohmic T06 and do that there as well. Okay, let's switch this to safety. We'll do one more. Okay, this is an Aerovox cap. Again, same genre, World War II, 0.0047 microfarads. And it looks like this one here is, it's only a 600 volt DC, so we're going to put 500 volts DC on it. So this is from a very low voltage transmitter. Okay, let me crank this back down to 1. Here we go. Okay, it's charged, and let's see what we get. Wow, 10 gig. That's 100 gig right there. It's at 150 gigs right now, so essentially there is 0 leakage out of this guy. This one's a definite thumbs up. We got another winner. Well, folks, that's about it. I appreciate you tuning in here today. You can see all the different things you can do here with a Megohm meter like this. Everybody should have at least one of these. My rule of thumb is you have to have 3 of each of everything. You got one that you normally use. Well, if it breaks, you have to have one to calibrate it against or to check it against. And then do you know whether that one works or not? So you have to have another one laid back again so you can fire that one up. And then when 2 of the 3 match, those are 2 good ones. And the one that doesn't match, that's the bad one. So you have to have at least 3 of every piece of test equipment. Again, thanks for watching. Hopefully we'll see you soon.